Good afternoon, everyone. I think let's get started. I think this is going to be more like a discussion session, but it's more than the number of students I expected. I thought like maybe less than 10, but there are like 12 students. It's amazing. Okay, so maybe let's get an idea of like how many of you here know pointers already. Okay, at least half of you. Okay, so for the benefit of the other half of the class, we'll just start with the basics of pointers, okay? And then we will go into seeing like how pointers are actually, how will we be using pointers in modern C++, okay? I mean in C++ 11 and 14, we will not be using the idea of pointers or the concept of pointers in a very similar way as we do in C programming. So I think most of you would be aware of pointers in C programming, right? Or pointers used in C. Okay, maybe let's get started right now. So just before we start, this is one of the like topics that I like the most in C++ programming, because like it's actually so powerful and it needs like a complete, like a very good understanding to get things working with pointers or to code with pointers. So this is one of my very favorite topics. Okay, so we're going to start with pointers. So till now we were talking about variables. We get type of the variables like an integer variable which you can store an integer. We say like int num. This int num can be made to store an integer, let's say the value of 5. When this like what to say, this simple piece of code, when this is executed in your C++ program, what happens in memory? Assume this is memory, okay? Now we are going to the low level details of what is happening inside the computer's memory. Inside your memory, so you can think of your computer's memory as just like a byte addressable array. By a byte addressable array, here we mean, in this simple example, let's just think our computer's memory has just addresses 0, 1, 2, 3, 4, 5, 6, 7, maybe like, okay, just maybe 8, maybe 9, okay. There are just 10 bytes in our computer's memory. This is a very simplistic view, and in this view, if you think about this, when you like create an integer variable called num, a part of this memory is reserved for this particular variable, okay? So integer variables in turn takes like 4 bytes of storage internally, okay? This is like the usual thing. It takes 4 bytes of storage. And if each of this box here is a single byte of memory, then this variable num can be allocated anywhere in this 10 bytes. Okay, assuming our program has access to this entire 10 bytes of memory. So what can happen here is like, let's say these 4 bytes from 4, 5, 6 and 7, okay? These 4 bytes of storage will be allocated for the single variable called num, okay? And we will just name the variable like here, okay? This particular memory is called num. So which means num is an integer variable with 4 bytes of storage, and the starting address, okay, the starting address of where this num variable is allocated is from address 4. Okay, so according to this particular program, now the variable num is stored at address 4, and the value of 5 is stored inside this place. You can think of it like this. So it will be just like most of the space will be, I'm just storing 5 here, but it will be more like 0, 0, 0, 5, something like that, okay? It will be, internally it will be just stored as 0, 0, 0, 5. And 4 bytes are needed just to make sure that we store like, we can store like large enough numbers, okay? But for a small number like this, entire number will be just stored in one of these bytes. That is enough for this number. And now, if at any point in our program, if we want to get the address of this integer variable num, we can create a special type of variable called a pointer variable. We can just say, I'm going to create pnum, okay? Pnum is a pointer variable, and it is going to point. How can we say that this is a pointer variable? It's just by saying an asterisk here before that pnum in the declaration. Pnum is a pointer to an integer. You just write the type of the variable that it is going to point to like this, okay? So this particular line just says pnum, this is pointed to an integer, pnum is pointed to an integer. And when you create this pointer variable, you can directly initialize it to the address of the variable num. Okay, so at this point, at this line, what is happening is address of the variable num is taken from the memory of the system. Now, in this particular simple example, what is the address of num? 4. The address of num is 4. Even though num spans across 4, 5, 6, and 7, only the starting address of that variable is considered as the address of that particular variable. So, in this particular case, since 4 is the starting address of where num starts, this particular ampersand num will return the value of 4, and that will be stored in a pointer variable. Pointer again takes some memory. Let's assume let's maybe assume like some bigger memory. Okay, somewhere down the line. Okay, somewhere down the line, we would have created a pointer variable here. Okay, and would have named it pnum. And in this pointer variable, we would have just stored the address of that particular variable, address of num. So address of num in this case is just 4, right? Just to not get confused with the addresses and integers, what we will say is all addresses are usually in hexadecimal. Hexadecimal numbers are represented by 0x as the thing. So you can think of all these addresses as 0x1, 0x2, so that we don't just get confused with an address and a normal integer value. Okay, something like this. It's in hexadecimal, and so this particular pnum variable, now just the value of the pnum variable, which is a pointer, is just the address of the variable num. So what this means is, using this pnum variable, now we are actually referring here. We are actually, from this pnum variable, we are actually pointing to the variable num. What do we mean pointing to? With this pnum variable, now we would be able to actually access the num variable. How can we do that? If you just say std cout, okay, pnum. Can someone say what will be printed here? For this example, what will be printed here? If you just try printing pnum. 4. It will be just 0x4, the hexadecimal value of this address will be printed. And if you try printing std cout, if you just print like an asterisk pnum, it just means, okay, pnum is a pointer. This asterisk here stands for dereferencing operator. Now I'm going to go and fetch the value, okay, that this pointer is pointing to. This pointer is just pointing to the num variable. If you just print pnum, it just prints the value of this pointer. But if you just print star pnum, it prints the value that this pointer is pointing to. So in this case, star pnum just prints the value 5. This pnum just prints the value 0x4. Does this make sense? It's like very simple in a way. Like this syntax is also familiar to us from iterators, right? In iterators, iterator, if you want to like go and access the element inside the iterator or print an element inside the container like a vector, you will say like asterisk it, which means like using the iterator we are going and accessing the elements inside the container. Any questions about this? Whatever we are doing here. But can someone tell me like why is this even meaningful, in the sense we already have the variable num? Why would we even want to take the address of that variable and store it in a pointer and then print the value of 5 with using this pointer with so complicated syntax and stuff like that? We could have directly just printed num, right? If you want to print num, you could have directly printed num. And if you wanted the address of num, you could have directly printed ampersand num. Ampersand is just called the address of operator. It's called the address of operator. So we could have just did these two things for getting value of 5 and 0x4, right? But why did we do all these things? Anyone? Yeah?
That's by reference to function with the non-object.
Yeah, but in C++, if you wanted to pass by reference, you already have the ampersand. The passing by reference is separate model, right? You could have done that, right? Anyone? Okay, in this particular example, actually this is meaningless, okay? By meaningless in the sense, it doesn't make any sense to create a pointer or just a normal integer variable, okay? And then access the actual integer variable using the pointer. It is actually not so useful, or you wouldn't see any code like this, but this is how we can get started with understanding pointers. So pointers is a pointer is a variable which stores the address of some other variable, okay? But the type should match in a way like, okay, we are saying in this case pnum is pointed to an integer, so it can only store address of an integer. If you had said like cat star like p some character pointed to a character, then that particular pointer will store the address of that particular character variable. We need not go into those details right now, but with this, the reason why pointers are useful, okay, in C++ is, till now, we had a very simplistic model of memory, okay. When we say memory, if we are saying this variable, the int num again, okay, int num, and if we say like num is equal to 10, okay, this variable, if this code is inside main, is created on a part of the memory called the stack. So we have two types of memory here. So one is the stack, okay, and the other is the heap. So till now, whatever like local variables that we are creating inside any functions like main or any other function will always be created on the stack. That we mean in this particular case, this piece of code, these two lines, just create a variable called num and assign a value of 10, and this is on the stack, okay? By on the stack, what happens if a variable is on the stack is when the function goes out of scope, if main ends or some other function where the variable is declared ends, when the function goes out of scope, these variables on the stack are automatically deleted, okay? They are just gone. But at the same time, we can do something else, okay? If your program, while it is running, okay, dynamically, if it needs some memory, okay, while it is running, your program decides, I think I need like, let's say, I need to store 100 integers. When the program starts, the program wouldn't have any idea how many integers that the user wants to sort, okay? In that particular case, the program wouldn't have any idea how much space should I allocate for that. So in that particular case, if we want to let's say create 100 integers after the program has started, we would have something like, okay, we create a pointer variable int star p, okay, so p is a pointer to an integer, and we will just say the line would be the new So this particular 100 could have been got from the user and stored in a variable, and that variable can be used here, okay? So now this line of code, okay? So till now we didn't see any keywords like this new. So here what it is saying is, on the right hand side of this statement, create some new memory for me. The program is asking the operating system to create some memory, or to have some memory, and the memory needs to store 100 integers, okay? Memory just needs to store 100 integers. In that particular case, what would happen? The new memory that this program is requesting will be created or will be made free for this program to use on the heap, okay? This memory will come from the heap. You can think of actually it will be from for 100 integers we would need 400 bytes, because each integer takes 4 bytes. So 0 to let's say 399, this 400 bytes of memory, okay, this 400 bytes of memory would be created on the heap, and the first address of this memory, maybe let's just start this at 1000, okay, and this is 10001399. Because the addresses 0 are usually reserved by the operating system, and so if it's giving you the memory from 1000 to 1399, okay, 400 bytes, what happens here? The variable p that we have here will still be created on the stack. Okay, the left hand side is the stack and right hand side is the heap. Variable p is still created on the stack, and all that variable p will contain is just the first address of this 400 bytes of memory, which is used to store 100 integers. And the first address in this case is 0x100. So now this means, because of this equal sign, okay, first this operation happens, first the memory allocation happens, this is step 1, and then pointer variable is created, step 2, and third, this assignment happens. By assignment here, this is created, a pointer variable is created, 1000 is placed here. After 1000 is placed here, what it means is like this variable just points to the first byte in that particular memory. That's it. And without pointers, we would not be able to store any memory addresses. Okay? And if we can't store any memory addresses inside a variable, then we cannot use the memory that we can dynamically allocate when the program is running. And this is the use of pointers. This is why we need pointers. So if someone, like what to say, whenever if some later explain pointers to someone, please don't stop here. Okay, if you explain pointers to someone in the future, please don't stop with this example, because it wouldn't make any sense for the person who's trying to understand. So this is what is actually needed. Okay, so you create some memory dynamically on a part of the memory called the heap, and whenever if you want to access this particular memory, you need to have the starting address of that particular memory, and to store that starting address, you have a pointer variable which stores it. And after this, you can directly use this memory as an array. But since this is pointed to integer, hereafter you can just say p of 0 equals 10. P of, let's say, the last thing is like 99, right? P of 99 is equal to 70, something like this. You can directly access this thing as an array. Okay, you can access this memory as an array, and your program would work fine. Any questions about this? Feel free to ask any questions, because if you haven't been used to pointers before, it may be so different. Okay, is everyone was everyone able to understand whatever we saw till now? Okay. So yeah, now let us see some code. Same. Now let's just do the same example as we did here. In star p equals new, like 100 integers, okay? And then if you want to access these 100 integers, you just write a for loop. Says goes till 100, goes till 99, and you can just say p of I equals, let's just place the value of I, the index itself, inside that thing, and then if you want, we can just try printing this. So just make sure the element is like what is it, that stdc out. You want to print the, let's just print the address also, okay? So how will we print the address in this case? I want to just print the address of all the different 100 integers in this case. How can we do that? Yeah?
You put an ampersand before it?
Yeah, you can just have before printing this p of I will just refer to that particular element, and just add ampersand before. This gives you the address of that particular element. And then after that, maybe have some delimiter, and then just print the actual element p of I. 10 integers, okay? Instead of 100, let's just make them 10. Okay, now let's see what's happening. So you see this? So at least you can believe I was not just like, let's say, fooling around something. The actual pointer, this is the actual address, okay? So your program has got, like in this case, 40 bytes of memory, okay? And the first integer is just stored in this particular address, 0x. There's so many hexadecimal, all these hexadecimal digits, and there will be, like in this case, I think there will be like 48 bits in this case. It's for a single address. You need like 48 bits for storing that. We need not worry about those details, but this is just the address of the element, and this is the value of the particular element. Okay. And after this, now in this case, there is a problem with this particular program. Okay, so assume this program we have like dynamically allocated like 10 integers, space for 10 integers, which is 40 bytes, right? But at the end of the program, we just exited like normally. We did not do anything with that memory. So for the memory that is created on the stack, you need not worry about freeing that memory. But for the memory that is created on the heap, okay, as programmers, we should explicitly free that memory. Else, what will happen is, if this particular program has been running, like what to say, continuously, okay. If this program has been running continuously, for example, if this piece of code, if you're writing some piece of code for like a Google search engine, which is like on all the time, right? If you write some code like this, what will happen if this code is kept on like being called again and again? Every time like 10 integers or like 40 bytes of memory is being created, and that memory just stays on the heap forever. By forever, we mean like till this program actually terminates, okay? When the program terminates, the operating system actually cleans up, but for programs that will be running like for a longer duration, this is actually a problem. So, whenever we dynamically allocate memory on the heap, it is the programmer's responsibility to actually go and delete that memory, okay, or free that memory. So, how can we free this memory? Is we have the pointer p, which points to the first byte or first element in the 40 byte array, right? So we can just say, and since this is an array in C++, we can just say delete that pointer. The syntax is like this. You have to say delete with a array sign, because it means like it's not just a single variable, but it is like an array of integers. P points to an array of integers, and so we are going to delete the entire thing using this syntax, okay? If we had just created like a single integer variable here, some like this, okay? If we can do this also. This just means a single integer variable, space for a single integer will be created on the heap, and that particular address is stored in P. If this was how we allocated memory, then that particular memory can be deleted just by saying delete P, okay? So in C++ we have this distinction between like what to say, how it's easy to see if you have, when you are using new, if you have used like the array subscripting sign there to create an array of some objects, then you just use the delete of the array subscripting sign to mean that it is going to delete the entire thing. If you intermix this thing, it is like undefined behavior, okay? So anything can happen, your computer may even crash. Yeah, so with this, we have like allocated some memory for, let's say, some integers, okay? And we can do the same thing with, let's say, we can create a new class. Like a point class. And okay, after creating, you have a point class right now, and you can just have things like, okay, I think I'm not going to write code for this. I already have some code for the point class. I'm just going to copy and use this, okay? Just for the reason of time. Save some time. Okay, so this point class just has two like x coordinate, y coordinate, assuming both are like integers. It has a constructor, default constructor. It has like a parameterized constructor. Very simple. It has get x, set x, get y, set y, and let's say a print for the point. Okay, and I'm going to copy the CPP file also. So here in the definitions we have like get x, set x, get y, set y. The default constructor creates a point with x and y coordinates 0 and 0, and we have the parameterized constructor, and we have print statement which just prints like x comma y with like brackets around it. Okay, and now if we want to create, okay, after this let's go and create like some points. Okay, so I want to create so I'm just going to create a point, point B with, let's say, values 3 and 4. Okay. Now if you want to print this point, we usually do print P dot okay, so I just used the same thing here. We used P before, right? So let's just name it as PT for the point. Okay, we just used P for the like pointer variable, so you cannot use the same variable again. So I'm just naming it as PT. Okay. So now we just created this point and we just printed that point. Can someone tell me where is this variable point created? Is it created on the stack or on the heap? The memory for this particular variable point, is it created on the stack or on the heap? Stack. We did not, until we use new explicitly, okay, that particular variable will be created on the stack. So in this case, point is just created on the stack. Okay. Now, what we can do is we can create a. I'm going to create a pointer to a point. Okay. This is PTR pointer to a point variable. Pointer to PT, okay, this is like a pointer to the point, okay, and here we can just store the address of PT. Okay, we are just storing the address of this point object that we just created in this pointer variable, and now we can again print the points details using this pointer, but since this is a pointer variable, the syntax is slightly different. Hereafter, we will not be using the dot notation for accessing the member functions or the data members, but instead, from a pointer variable, if you want to access a class's data members or member functions, you will use the arrow notation like this. While reading it, it is also called dot. When you read it, like programs read it as dot, but it is this arrow sign, okay? Pointer dot print. So now let's see if the same point is printed again. So can you see this? We have printed point 3, 4 using the point variable itself, and we have printed the same point 3, 4 using a pointer to that point variable. Okay? Any questions about this? Now, where is this variable pointer to the point created? Is it on the stack or on the heap? Stack. This is still on the stack. This is still a local variable in this particular function, so it's still on the stack. Okay. But now what we can do is we can use the same pointer to the point variable to point to, okay, to a different x comma y. Okay. New, I'm creating this point. Maybe it's wrong, like use of the class. I mean, like since I just have a class called point, it's so like point, pointer, so many things I just about point. So if I'm going to create a thing like this, now what is happening here? first right hand side. Now a point object is created on the heap. Now in this line, a point object is created on the heap, and the address of that point object is returned by this new operator, and it is stored in this variable called ptr point. Okay, ptr pt. And now if we just print ptr dot print, now this is going to print the point 4, 5. You see that 3, 4, 3, 4, and then now, so using the same pointer variable, at this time in line 25 it was pointing to the point 3, 4, and at line 29 it's pointing to a different point at line what to say? Sorry, yeah, the point with the values of 4, 5. Now can someone tell me what will happen if we do this? 7, 9. Is this okay to do or not? So what I'm just doing, after that I'm just going and creating some more dynamic memory for another point variable, another point object with values x and y as 7 and 9 respectively, and again printing that point. Is this code okay, or is there any problem with this code?
You lose the reference to the first memory you allocated, so there's no way to free it anymore.
Cool. So the thing here is, okay, the problem here is we created a point with value 4, 5, right? So and that would have some address, and we have stored that particular address in the variable called pointer to the point, okay, ptr pt. But in line 33, when we just created a new point and just assigned that variable here, what has happened here is, after this line, okay, you cannot access that old point 4, 5 because there is no address. Objects in the heap can only be accessed using pointers, okay? But you here what you just did is 4, 5, 7, 9, right? So here what we just did is, initially in the heap, this is the heap and this is the stack. On the heap you created a point, let's say with 4, 5, and the address of this is, let's say 0x100. This is stored in the pointer variable ptr pt, okay? Now this was pointing here because it had the value of 0x100, and in the line when you just told ptr pt equals new point of 7, 9, what you just did was you created a new point, okay, 7, 9 object, and now this would be at some other different address, let's say 200, and what you did was you just overwrote this value with 0x200. And so what happened, this particular link is gone, now this pointer started pointing here. It's okay, you cannot access that, but there is also a problem of hereafter you cannot free that memory at all, okay? Hereafter, the first point that we created at 0x100 cannot be freed because you have no pointer variable pointing to it. Unless you have a pointer variable pointing to that first thing. Now this is a memory leak. So now this particular memory has been leaked in our program, and this whole thing, okay, is a memory leak. We have leaked memory here, and the same thing will happen if you don't actually free the memory explicitly. In your code, if you don't free the memory explicitly at the end, the same thing will happen. So now should we use delete, just delete, or delete with the square brackets to delete the pointer to point? Should we use this or this? So you should just go and look at the new. So new is just creating points. It is not creating an array of points, okay? And so it's enough to just use this, just delete ptr. Not it's enough, it's correct. It's correct only to use this. If you use the other thing, it's undefined behavior. Okay, any questions till now? So at a very high level, if you think about it, till now we were using only variables on the stack. If you want to use variables on the heap in C++, you use the new operator. The new operator allocates memory for you based on the type of the object that you are allocating, it will allocate so many bytes of memory for you on the heap, and it will return the address of the first. I mean, if a bunch of memory is allocated, then it will just return you the address of the first byte of that particular memory, and you can store that particular memory in a pointer variable, because pointer variables are basically used for storing memory addresses of other variables. And once you have that pointer variable, using that pointer variable, you can just access the object, but with some different syntax, using the the arrow operator. One very useful scenario for having pointers in C++ is if you want to create a linked list with the head. Okay, if head points to a node with value 10, and if this node points to another node, and this goes on. I hope everyone here have an idea about linked list, right?
Yeah, so, well, maybe you can also have a tail that points back to the head too.
Yeah, we can also have like a tail pointer that is pointing to the last node in the linked list. This is also, yeah, we can also have it like this. But yeah, so this is like a linked list, and in C++, if you want to like create a linked list, this particular, the next part of any node will be a pointer. Okay, so if you want to create a linked list like this, if you want to create a class for this particular thing, actually I already have wrote that. If you want, you can just take a look at it. I just node like a node class. Okay, this is like a node in the linked list. It has some data, and it has, see this line. Okay, it has a next variable, and this next variable is a pointer, and it points to a node of the same type. Okay, so that's called like node star next. And then you have a constructor for this node, and you have like a get node, get data, get next. So get next in this case returns a pointer to a node. Then we have set data, set next. Set next takes in a pointer to a node. Okay, and in the CPP file we just have these things like this is how a node is created, this is how you get data, this is how you get next, this is how you set data, this is how you set next. This is like pretty straightforward, and with this I was just actually like what to say. So if you just look at this particular piece of code here, okay, just focus on this. Here, what we can do is like I'm saying I'm creating a head which is a pointer to a node, and I'm assigning a null pointer to it. Null pointer, nullptr, is the C++ way of saying like this particular pointer is not pointing anywhere. Okay, it's not pointing anywhere. In C, this would have been just in caps null, null. In C++, you'll be using null pointer. And yeah, so here we are creating 3 nodes with values 10, 20 and 30, and while creating these 3 nodes, the next pointers of these 3 nodes are just assigned as null pointers. These 3 nodes are created with the names n1, n2 and n3, and all these 3 are actually pointers. And then using these 3 things, we are just saying n1.set next n2, n2.set next n3. Then we are saying the head is nothing but head starts at n1. So now, after this piece of code executes, okay, there will be a linked list that is created with n1, n2 and n3 in the same order, and head will point to n1. And using that particular head, you can go and print this list. So since we don't have time to like write these things in class, I'm just showing you like this is how like linked list is implemented in C++. Okay, and this is like a very basic implementation, just like for the pedagogical purposes, I just had like, just 3 nodes and stuff like that. But usually it will be like, there will be a node class, there will be a linked list class. The linked list will actually manage the nodes, and in main we will be just creating an object of type linked list. This is very similar to how you would have done in Java in 367. Okay, but this is like we can also do it like this. This is also a very simple way of doing this. And if you want to go to the print list and see how it works, so here I'm just saying. There is print list takes a head, right? Head is nothing but a pointer to a node, and while p node. So this just checks if the p node is not null. Okay, this just means while p node is not null, if it is not a null pointer, then keep on going, go and print, see out, print the node's data, and then print the node's next pointer and then print some some formatting things, and then this line just says go to the next node. P node is to P node dot next get next, okay, and this keeps on going. And if you run this, yeah, output would be something like this. See here, I usually like printing a linked list like this, exactly as if it is a linked list. So if you see here, 10 is the data, this is the address of the next node, and there is like, I just printed this, and so there is like 20, address of the third node, 30, and 30 is the last node, and it has a value of null pointer, and null pointer's value is just 080. Address 0 is the null pointer's value, and it points to null pointer. There is nothing after that, okay? Okay, after showing you all these things, if you want to create a linked list in C++, please don't do something as we just saw now, okay? I mean, this is just like to explain like why pointers are useful, but if you want to create a linked list in C++, the standard library again provides you like a thing called forward list. Just go and use that. It is a singly linked list, okay? Don't recreate or reinvent the wheel by creating linked lists in C++, unless it is like for some programming assignment purpose or something like that, okay? And yeah, with all these things, now what we are going to see is, even though we saw about this new and delete in C++, in modern C++, if you go and work in C++ 11 or 14 in any company, you will not be explicit, we should not explicitly use new and delete, okay? Because C++ has now come up with things called smart pointers, because this particular thing we are telling you delete, always remember to delete the memory that you allocate. That is such a huge problem with developers, because developers, programmers, we usually forget that. Because it's not like a simple program here. You would have allocated some memory, you would have passed that memory to so many different functions, and finally it is your responsibility to free that memory. And it's so easy to forget this, and so many bugs are just created by memory leaks. If you're like, when your program just starts running in, let's say, in some servers, suddenly the server will crash, and finally they will find out the reason was like one person has just forgot to free a memory that they have allocated, and that particular function was being called like 1 million times. And every time it was called, it was allocating, let's say, like a chunk of memory, 4,000 bytes of memory, and so it keeps on going. And after, like, it will not be evident immediately, it will be evident only after, let's say, a month, okay? After a month has gone, your program will crash, and then they will come and they will like find you, okay? Say like, okay, you remember that you should actually free your memory that you allocate not keep, okay? So to avoid all these problems, what C++ like what C++ has done is, like, if you want to create some pointer, don't go and use like the new and delete thing. Instead, what you will do is, you will first include memory, okay? There is a header called memory. This is the only thing that's needed for all like smart pointers thing. We are going to create smart pointers here, okay? STD, the first type of smart pointer is called a shared pointer. We are going to create a shared pointer for the point type, okay? We're going to create a shared pointer for a point, okay? And in this particular case, we will remember we are not saying it's point star, because shared pointer itself says that this is a pointer. This is going to be a pointer. So shared pointer SP, let's say SP1, okay? And this SP1 is going to point to some dynamically allocated memory, right? And this is just like very similar to saying std vector of in something like that, okay? It's just in the standard library. We're creating shared pointer of point, and the name of the variable is SP1. SP1 is the pointer, and in the constructor, okay, while creating this object SP1, you just give the dynamic memory, you just give that resource that you want to create. Let's say new point of 10, 20. We are creating a new point, okay? We are creating a new point, and that memory of this new point with values 10, 20 is pointed to by SP1 from this time on, okay? And so now what will happen is SP1, okay? Now you can just go and print SP1 dot print. Very similar to how you use this PTR-PT. PTR-PT is a raw pointer that we created. Now SP1 is a shared pointer. This is a smart pointer. And after you do this, let's see if it prints the same thing. I mean, 10, 20, the point 10, 20 should be printed. You see this? Using the smart pointer, we are able to access the point that we just created in the heap But what is missing here is that you need not worry about deleting that particular point, deleting the dynamic memory that you allocated. What is happening in this case? Because SP1, this is a stack variable again, okay? SP1 is created on the stack, and SP1 will be deleted when main ends. When your program comes at this line 45, SP1 will be deleted. And since it is a smart pointer, it automatically knows that, okay, I was pointing to some dynamic memory, and so now when I am going to be deleted, I will also free the dynamic memory, and then only I will get out of this particular function. Okay, so we need not worry about deleting this, and this introduction of like smart pointers in C++ has reduced so many like memory related bugs, like memory leaks. And if we are going to like start a new C++ project, please don't like use raw memory management. Try using like automatic memory management, which is like using the smart pointers. And here what is happening in shared pointer, why this is called a shared pointer is, we can go and create, okay. So you can just like take one more so we are just creating a function here, okay. So this function is called print shared point, okay. And what this is taking is, this is taking a, let's say this takes a, this shared pointer SP1 by a const reference, okay, by a const reference, and inside this particular function, one more shared pointer named SP2 is created, but it is created based on SP1. So what this means is, now SP1 and SP2 are pointing to the same dynamic memory, which is the point 10, 20, and after that we are saying, don't worry about this line as of now. First let's just see if we are printing 10, 20 twice. So we are not calling that particular function. So I'm calling this particular function print shared point and just passing in this shared pointer inside that. So the same point is being printed once using SP1, and the same point is also printed one more time using SP2. So SP2 and SP1 actually point to the same dynamic memory, okay, which is the point 10, 2. But what is happening here is like, why this is called a shared pointer is, when just SP1 is pointing to it, it will automatically have some like bookkeeping with respect to it. After we created SP1, if you just print this line, it says like reference count. We are saying, we are calling a function called use count. How many people or how many pointers are there for this particular dynamic memory, okay? And that is called sp1.use count. And when we just do this, see here, at this time there is only one person using it, okay, which is SP1. But if you have the same line within your function, after SP2 is also pointing to it, you would have ref count 1 and ref count 2. So when inside this particular function there are two pointers, SP1 and SP2, that are pointing to the same dynamic memory, okay. And after this function ends, after print shared point, after this function ends, if we try to print the same thing again, ref count, can someone tell me what it should be? 1, because that function ends, and so SP2 has gone out of scope. Since SP2 has gone out of scope, it will decrement the reference count from 2 to 1, and when it comes here, SP1 will also go out of scope. It will decrement that count to 0, and once that count becomes 0, immediately that memory in the heap will be deleted. And this is such an amazing idea. Like this is called reference counting for implementing shared pointers. See here, you say ref count is equal to 1, ref count is equal to 2, and ref count is equal to 1. And if you want to make that ref count 0 by yourself, what you have to do is like just say sp1 is equal to null pointer. So now you're saying I am making SP1 explicitly to become null pointer, don't want it to point anywhere. So after that, now if I go and use the ref count in that same pointer, it becomes 0. So this means that the memory that SP1 was pointing to, which was the point 10, 20, was deallocated or freed or deleted at line after line 57. It was deleted automatically. Now there is no pointer pointing to that particular dynamic memory. Does this make sense? And this is how you use like shared pointer. And shared pointers, you can like, if you are sure that okay, multiple people will be pointing to the same object, okay, throughout my program, there may be multiple pointers pointing to the same object, then you will be using shared pointer. But if you are sure that okay, this particular piece of memory should always be pointed to by only one person or like one pointer, then you have another type of pointer called unique pointer. And unique pointer actually means we can do the same thing, unique PTR, okay? And in a unique pointer for a point, what UP1, the unique pointer 1, you just say new point of 100, okay, we're creating a new point here. So now this means UP1 points to this point and you can access the point using UP1 dot print. But after some time, if you want to create one more unique pointer, very similar to how we did with shared pointers, UP2, and just pass UP1 there, okay, and try saying UP2 dot print. If you try doing something like this, okay, now we may be thinking that okay, UP1 and UP2 are pointing to the same dynamic memory, which is the point of 100, 200, and we can print these two things. But if you run this particular code, it should not work. Okay, it says like call to implicitly deleted copy constructor of unique pointer. So we have not covered copy constructors yet, which we will be covering next class. But here, what is just happening is we are just trying to copy the contents of UP1, which is that pointer variable of this point, okay, the address of this point from UP1 to UP2. We are trying to make two things point to the same memory. But in a unique pointer, at any point in time, there can be only one owner or only one pointer can point to that particular memory. And so, since we are restricting that in such a way, you cannot do this, okay, this is not possible. But in C++11, from C++11, they introduced something called move semantics, okay? And in move semantics, now what we can do here is, I'll just show you quickly. So what we were actually trying to do was, this is that point 100, 200 in the heap, and you had like UP1 here, and you had UP2. And in UP1 was pointing here, you also wanted to make UP2 point here, but this is not possible in unique pointers because only one person can point to this memory at a time. And so you cannot copy something like, okay, I want to create UP2 with UP1, okay, you cannot do something like this. And instead what we can do is, when creating UP2, you can just say, I'm going to create UP2, but I'm just going to move, okay, whatever UP1 was having to UP2. So this just means, if this was having the value of, let's say, 1000, this address was 1000, okay? Now this moves this value here, 0x100, just goes here. Now this starts pointing here, but this is immediately made as null pointer. Okay, and so this makes sure that at the time, now only UP2, the unique pointer 2 is the owner of this particular memory, and UP1 is now gone. By gone, mean it just points to null. So when you go here in the code, instead of doing this, like this just actually copies it, okay? This is very similar to saying UP2 is equal to UP1, okay? The brackets is just similar to saying this, okay? So instead of doing this, now you have to do a move. So this move just means UP1 is giving up the ownership to UP2 of that particular memory. And so from this point on, UP2 will actually print. UP2 will actually own that particular point, 100, 200. So if you try to print using UP1 again, now it will be a Now this will be a segmentation fault. So this is a segmentation fault here. If you can see here, process finished with exit code 11 and the signal 11 is segmentation fault. We are trying to access a null pointer which is not allowed. Operating system immediately kills your particular program. That has just happened here. To make sure that that has happened, we can just say if UP1. If UP1 is not a null pointer, then print the particular contents, okay, like this. Then print this. Else, if it's a null pointer, then just say UP1 is something like this. That's it. So if you just do this, we can just make sure that if UP1, if you can see here, UP1 is null pointer at this time, so UP1 is null pointer. And I think it's like already 5 minutes over. But I just want to like say, if you are free, if you want to like leave, feel free to leave, because I just want to say like one more thing about you, and we are also recording the video, so you can watch it later also if you want. Since we are saying like we should not allow like what to say, new and delete, right? What they just made for this is like this particular line again uses new, which is like a naked new, and there is like a slogan in C++, 11 and 14 saying like, okay, there should not be any naked news and deletes in your code. You should not allocate memory by yourself. Just to avoid that, what they did is like the same thing. You can, instead of saying new, you can just say something called, there is a function template called make shared. You can just say I want to use this make shared, use this particular function for a point, and 10, 20, this just does the new for you, okay? Make shared of this thing, so that in your code you can actually not, if we are saying like, okay, we are going to use smart pointers, and when a new person comes to your company and say like, okay, you are saying like we should not use new and delete, but I can see new in your code base. You are actually allocating memory by yourself. Even to just avoid those scenarios, like you can just have it like, okay, make shared of point, this actually creates a point of 10, 20 in your heap and just returns the shared pointer for it, which is now stored in USP1. And in a similar way, we also can do for this, we can just have a make unique. That is a thing called make unique. We can just do it here in this case. But make unique is just made available only from C++ 14. So if you're using make unique, you should have like -std is equal to C++ 14 while you're compiling your code. With just C++ 11, make unique will not work. That's it, guys. So even though we learned about new and delete, just make sure that if you're working on modern code bases, always use smart pointers. And the two smart pointers that are very useful are like shared pointer and unique pointer. There are like two other things called weak pointer and auto pointer. They're not so used, okay, frequently, but you may want to take a look at those things for like a deeper understanding of what is going on there. Okay, thanks guys, thanks for coming, and I hope you have a great Thanksgiving break.